Hello, my name is Joel Adams. I'm from the Department of Computer Science at Calvin University. This presentation is about seeing and or hearing algorithm behaviors. Our project, the CSinParallel project, is to provide training and tools for CS faculty who want to inject parallelism into their courses. That's needed to take full advantage of today's multi-core CPUs. We've led 25 faculty development workshops since 2012. We've created a variety of tools, two of which are the ThreadSafe graphics library for creating real-time visualizations and the ThreadSafe audio library for creating real-time sonifications. To give you an example visualization, if we wanted to compute the integral, the sine of x dx from 0 to pi, the answer for this is 2. A computer program typically does this through an approximation technique. So what is that technique? Well, we can illustrate this using TSGL using the trapezoid method, where the function basically draws trapezoids from the x-axis up to the sine curve, sums those trapezoids, and the combined sums are an approximate value for the integral. So in this case, a single thread did all the work, single core, and we draw those in the same color because it's one thread. If we were to do this with two threads, we give each thread a different color and we can see the division of labor, and this goes in about half the time. And if we were to do it with four threads, now it goes in about a quarter of the time of the original thing. So TSGL lets us visualize the parallel behavior and experience the speed up. Visualizations are valuable, but they do have some limitations, particularly for students with visual impairments, and it can be challenging to create visualizations of some algorithms. Sonifications may be more useful in these circumstances. So we're going to go through a simple example calculating n factorial. This is the historic mathematical definition. It's a recursive definition in that we compute n factorial as n times n minus 1 factorial. The traditional approach is to use a loop, and so here's a C++ main function that calls a factorial function and outputs the result. Here is a definition of the factorial function that uses a loop. And if we were to sonify this, we can use TSAL to create a mixer object that's like a DJ's soundboard, create a synth object, add the synth to the mixer, and then pass that synth to the factorial function. Inside the factorial function, we compute a MIDI note each iteration of the loop, and we scale the value of that note to the value of the loop control variable I. Once we have that note, we play it for half a second using the synthesizer. The key principle here is that if we have an iterative function like factorial, for each iteration I, we play a note scaled to the value of I. So now, instead of the usual silence, we instead get that is, we can hear the factorial function doing its work. In this loop-based version, we hear the loop iterating. But if we were to use the recursive version, make some space, create the synth parameter, create a note that's scaled to the value of n, the value on which we're recursing, play that note before and after the recursive call, and when we reach the base case, temporarily stop the synthesizer, just so we get a break. Here, the principle is that for a recursive function, we play a note scaled to the n, the value in which we're recursing, before and after each recursive call. Again, if we call this function same way as before, the traditional approach will give us silent behavior that's indistinguishable from the loop-based approach. But if we do this with the sonified version, we hear something quite different. Did you hear that was twice as long because of the recursion winding from 5 down to 1 and then back up from 1 to 5? The recursive version takes twice as long because the recursion's winding and unwinding behavior. That motivates the use of a different recursive technique called tail recursion that cuts out the unwinding phase. And that approach is as fast as the loop-based approach. So sonification lets students hear how recursive behaviors differ from one another, how they differ from loops, that provide extra information that's useful. Spectrograms are visual representations of sound sequences. They chart the frequency on the vertical axis against time on the horizontal axis. So here are 3 spectrograms, one for the loop-based version of factorial, looks like ascending stair steps, one for the simple recursive version of factorial that looks like descending and ascending, and one for tail recursive that looks like just the descending stairs. We can create other sonifications for other kinds of control structures besides loops, different searching algorithms, linear and binary search, sorting algorithms, sequential versions of algorithms versus parallel versions, exceptions being thrown or caught, lots of different things you could sonify. The examples we presented have been in C++, but the ideas we presented here are language independent. So, do visualizations and sonifications improve learning? We've conducted multiple randomized controlled experiments, and the answer has been yes. In each experiment, we had a control group in which students would complete interactive exercises using traditional software, and a treatment group, which were the same except the students used either visualization or sonification software. To assess the effects, we gave students a quiz 2 weeks later to test their long-term retention and understanding of the concepts. And the treatment groups consistently and significantly outperformed the control groups in these experiments. So here you see the results of our most recent sonification experiment. So in conclusion, visualizations and sonifications provide extra information that seem to help students build more accurate mental models of computing abstractions. TSGL and TSAL may each be freely downloaded from GitHub at this URL. My contact information is adams@calvin.edu. And I'd like to thank IUSE for their support, which made this work possible, my fellow CSinParallel PIs, the many Calvin undergraduate students who worked on this project, and you for your kind attention. Thank you.